So good afternoon, everyone. Thank you so much for joining us. We have been having a few technical difficulties as usual on our end, but things seem to be going and taking off pretty soon. And yeah, thank you for taking out the time, and let's get this ball rolling. So myself, I'm Sonali Kamble-Müller. I am the Innovation Advisor at Innovation Center Denmark. We are based at the Consulate General here in Munich. And with me, I have joining Ulrich Olsen. He's the Consul and Research and Innovation Attaché, also sitting with us in Munich. So before we jump into the very interesting presentations that we have lined up here, and we have over 70 participants, let me just quickly run through the agenda for the day and what we're going to talk about, who we have on board, and what the structure will look like. For that, I'll just share my screen. So I hope you're able to see what I'm talking about. So let's begin with all the technical delays on our end. This is what the day or the rest of the day is going to look like. We have welcome and introduction by Ulrich. He will be shedding a bit more light on who we are and what we do at the Innovation Center. Then we are, as you can see, we are sitting at the studio here at ASO Anwendungszentrum. It's a bit outside of Munich, and we have the host ESABIC Denmark here. So we are talking from their studio, and they will also formally welcome you and introduce who they are as well. And followed by that, then unfortunately, ESABIC Denmark is not able to join us due to some sickness reasons. So we will skip that part. But followed by that, we'll have a very interesting presentation by Peter Seystedt. He's from the Ministry of Higher Education and Science of Denmark, and he's like the key person in making the space strategy, the national space strategy. So he'll be putting a few words on that. And followed by that, we'll have all the company presentations, all the pitches, all the interesting work that you guys are doing, and all the audience out there, please take notes, take down your questions. You will have the chance to put up these questions in the Q&A round. Please use the chat function for that. My beloved colleague who's joining you, probably you spoke to her, Malu, from Silicon Valley. She's up quite early, so she'll be taking care of all your chat functions, and she'll be relaying the questions in the Q&A round. The discussion will look somehow like this. We have some preset questions which we'll throw to the panelists, but of course it's please feel free to write down your questions, and we are happy to convey them to the panelists. On that note, I would, without further delay, I would like to hand it over to my colleague Ulrich, who will then speak a bit more about ICDK.
Thank you very much, Sonali, and also a very warm welcome from my side and our side, representing Innovation Center Denmark. We are a global network, and today we are represented by the innovation centers in Munich and in Silicon Valley, as Sonali also mentioned. And my name is Ulrich Olsen. I'm the Consul and Research Attaché here in Munich at our innovation center here. So a few words about the Danish innovation centers. Since Denmark is a very small country, we have some global hotspots. Denmark is present around the world in 7 places, with the idea that we need to be present in some of the places where research and innovation and technology is in the forefront. And Munich and Silicon Valley are 2 of those. And this is also a partnership between the Danish Ministry of Foreign Affairs and the Ministry of Higher Education and Science. So we are trying to help Danish researchers, companies, organizations with internationalization when it comes to research collaboration, innovation, both the early stages, but also those parts of innovation that links more to the commercial side. And of course, incubation and startups is also in our ballpark. So we are very happy to be here in these facilities. This year, from the side of the Innovation Center in Munich, we have a focus on space, and we would like also with this event to dig into the very interesting ecosystems, both here in southern Germany, in Bavaria, and in Silicon Valley. So I'm also personally looking very much focused forward to this event. This is an innovation talk, as we call it. So it's a forum where we bring key and interesting actors together, and also with a global audience. So we're looking forward to see to learn something new, and to be inspired, and hopefully also have a lively discussion after these pitches and presentations. So that's it, I think, from my side, and stay tuned for much more.
Thanks a lot, Ulrich, for that wonderful beginning. Like he mentioned, the innovation talks, it's a series of dig-ins that we do where we deep dive into cutting edge technologies or topics. The previous one was on hydrogen, and now we are doing in-space manufacturing. So stay tuned for more content to come. May I please now hand over the mic to Thomas after a brief short introduction to ESA BIC and what they're doing here in Europe, promoting the space ecosystem, and we'll be right back.
Like space, your business's capacity for innovation is continually expanding. And ESA Business Incubation Centers, or ESA BICs, empower your business to realize its potential through the power of space-age tools and cutting-edge data, so you can dream even bigger. Harnessing both upstream and downstream technologies, we help turn promising startups and entrepreneurs into successful businesses. And it's more than just technology we help with. From support and advice to an attractive co-working space, networking, and up to 50,000 euros of non-equity funding, ESA BICs equip your business with all the tools it needs to take off. And with over 20 ESA BICs in more than 60 locations, you have local access to our huge pool of resources to help you grow wherever you are in Europe. Embedded in your local community and supported by your national government, our ESA BICs are connected to international industry, universities, and research organizations. And as part of the largest innovation network in the world, access to our alumni, partners, and investors keeps you connected. With over 900 businesses launched through ESA BICs and more than 200 million euros of investments in our startups, your businesses are empowered to thrive and grow. We're ready to hear from you. Apply to your local ESA BIC today to begin your journey.
Good afternoon also from my side. My name is Thomas Ballatry, and I'm happy to welcome you as well as the representative of the host, AZO, as the managing company of the ESA BIC Bavaria. Just give me a short minute to share the screen. There we go. So at AZO, we cover the whole value chain of innovation in the space field. We gained many years of experience in the different fields from innovation scouting over innovation ecosystem, hackathons, as well as incubation and acceleration. This is basically my task in the company. I'm responsible for the ESA BIC program at AZO. In Bavaria, we run this program with many renowned partners, as you can see here on this slide. We have managed to continuously grow, but not just ourselves, mostly the startups. Nevertheless, we are very happy that we will grow even further in Bavaria and will open 2 additional sites here soon. And with this, also welcome a few new partners to our partner network here in Bavaria. The startups that we have supported only in Bavaria. You can see some KPIs here. We have supported 189 startups so far, which have managed to raise a total of 1.3 billion euros of investments in total over the past recent years, which I think is a very impressive number, and we're really proud of this achievement of our startups. We have supported startups in many different industries. Here on this slide, you can see a few examples of one of our very successful companies. I believe that most of them, or even all of them, are known to most participants here today. You can see that we have two space companies present here, which also shows that the new space field is a growing industry in our program, in the companies that we support. And this is also the reason why we're happy to support innovation talks today on the topic of in-space manufacturing. We are the first address for innovative ideas, and we have the tools to do so. You've also seen it in the short introductory video, what the ESA BICs are doing. We have shown in the past that we are capable of supporting and growing, lifting the potential of early stage startups. And with this, I'd like to hand over to Peter from the Danish Ministry of Higher Education and Science. Thank you.
Thank you, Thomas. Just checking that you can hear me well. And Malu is nodding. That's a good sign. I'll just bring up my presentation. Just a minute. And good morning to Silicon Valley, and grüß Gott to Munich and surroundings. I hope you're well. And if my voice is failing a bit, it's because I was watching a great football match last night where Denmark qualified for the World Championship. So very important event, but this is more important, of course. My name is Peter, and I work in the ministry just mentioned. It's not a ministry for space, but we have a space division, and I'm sitting in it. I have been preparing the new strategy together with colleagues. I've been working in this area for now 5 years. I'm also delegate to the Danish delegation part of the Danish delegation to ESA. My field of expertise, responsibility is space exploration. So very pertinent. So what I'm going to talk about is the new strategy we just published this summer. I'll tell you why the link between space exploration and the green agenda has become so important in Denmark. And you might add that this is an old link, old news, because space has always been about sustainability. And you would never go to Mars without reusing materials or using local materials and trying to minimize the consumption of energy and other resources. Sustainability, and this is part of my main messages, is already inherent in everything that has to do with space exploration. But this sustainability, or green transition, as we say in Denmark, has become even more pertinent and visible and political. So it is important to establish the link now between sustainability and space exploration, which is in fact my conclusion, but I'll reach a conclusion when I conclude. But now you're warned, it is about sustainability. We had our first national strategy in 2016. This was the year, it's an important year, because this is the year we established our own first space division in the ministry. We had our own space law regulating everything going up. And this strategy was really a growth strategy. Its focus was on growth, and it was focusing on the big European satellite programs, or as we like to call it, the invisible space infrastructure. And one of the themes of this strategy was, how do we make this invisible infrastructure visible to society? This is, by the way, a theme we're still pursuing, because for some it's still invisible. You can't see the satellites, but we try to convince people they are very important to their lives. The strategy was then made by several ministries who gather in this space committee, interministerial space committee. So in Denmark, we don't have a space agency as in Germany, but we have a space division, which is part of the Ministry for Higher Education and Science. One of the outcomes, one of the pleasant and really groundbreaking results was that we joined this network of ESA BIGs, which Thomas just told you about. We did that in 2020, just before the arrival of a certain virus. But we managed to gather even to the DG, General Director of ESA. He's pictured here together with the former minister at the opening of ESA BIG Denmark. This is really one of the things that we are very happy about, joining this network. And we're trying now, and I think ESA BIG Denmark is doing a great job in building a real ecosystem for space startups. And this includes trying to attract new players, even non-space players, to the realm of space, which is not easy, but it has to be done. And ESA Business Incubator Denmark is playing a vital role in this regard. But then we arrive to 2021, which is another pivotal moment in, you could say, Danish political space history. This is where we transition to another strategy. And in 2021, the government published a new strategy, which was really a fundamental revision of the first strategic objectives. And the background for this revision was that the new government, supported by a majority in parliament, of course, had just published a new climate target of 70% in 2030. This was one of the toughest climate targets in the world, and I think it still is. The government used to say, we know how to get to 60%, but the last 10% points, we really don't know. We need new technologies. This Climate Act, together with many other policies at that time, meant that every sector, every policy area in Denmark had to contribute to meeting this target. It became sort of the new moon mission, just a very green one. And we had 10 years now to reach this target of 70%. So everybody had to contribute. And this meant that we also revised the space strategy, and we followed suit with 5 new objectives, which emphasized the contributions from space to the green transition of society. This was not a hard job, because as everybody knows, space and the green transition are very interlinked. You wouldn't know about climate change if you didn't have the satellites to tell you about the heating of the planet. But this strategy formalized the contribution from space to the green transition, to meeting the high target of 70%. And it did so by establishing 5 objectives just mentioned here. It was all about how do space infrastructure contribute to climate, environment, nature, biodiversity, sustainable cities, smarter cities, efficient public service, green value creation, and a 5th objective concerned security, because it had become very important in the realm of the Arctic waters. But I'll not concentrate on that objective today, and I even not concentrate on the 4 objectives here, but just narrowing in on this one, objective 1, because the challenge, and in fact, the challenge for me today, in order to make this speech, was to translate this strategy, which is very on the high note and very focused on satellite programs and what they can do for transport, energy, and agriculture, and to translate it into the realm of space exploration, the realm of in-space manufacturing. But I'll try and do so, and bear with me and follow me on this journey from this space strategy into space exploration. So we'll just go and talk about the Danish heritage here, because it is quite, we've been around, well, Denmark has been around for a long time, yes, but we've been participating in various exploration programs in ESA for a very long time. About the same time as we adopted the Kyoto Agreement on climate change, we also signed the intergovernmental agreement on the International Space Station. We've been members from the beginning. We've been participating in all the other programs that evolved. So quite a big heritage, been there around for some time. And here you see some of the high points in our exploration history. You see the astronaut Andreas Mogensen was in space in 2015, and he's going to go for another mission here in a few years' time. You see Perseverance on Mars, which has a lot of Danish contributions as well. On the right upper point, you see the Climate Observatory ASIM, which is situated just outside Columbus module and is measuring lightning, something which has really attracted the attention of many science publications. So I'm probably going to stay there for a while. And to the right bottom, you see drawings of Mars City by the architects Bjarke Ingelsbo Big, who are also today participating in space exploration. And today we are, as I said, part of the exploration program, which has now changed its name to Terra Nova. But we participate in various technology programs and support various technology developments in these, I assume for you, known programs. Expert, this is part of the exploration program, and the other GSDP and ARTIS are part of the more generic technology programs in ESA, and this is where we support Danish companies and startups. We even launched a private-public partnership in 2020. It's called Space Exploration Denmark. No points for creativity here, but it has proven to be an important vehicle for assembling, collecting interest and new partners who like to work on promoting the objectives of space exploration. And really, it's difficult not to be fascinated and happy about the present times if you love space exploration. This is a quote from ESA talking about space exploration renaissance. There is really a fever going on, not only in Texas with Elon Musk, but also in Europe. ESA is preparing a new ambitious program in space exploration, presenting it next year at the the conference where ministers meet to discuss the next 3 years budget. It will be in November 2022. And we are looking into a very exciting strategy from ESA side. And even EU, the union, has promoted space exploration and is contemplating even collaborating with ESA on space exploration, which was something quite new. ESA and EU have been working together on satellite programs like Copernicus and Galileo for a long time now, but it could mean that EU would also venture into space exploration. Looking forward to see what happens. But the question remains, and now I become somewhat Shakespearean. You know, there was a guy called Hamlet who was quite doubtful whether or not he should go this way or another way. So I think the question remains, and the question we ask ourselves, the existential question really, we ask ourselves in these times, and certainly in Denmark, why should we invest in space exploration as we fight climate change, as we really have a very urgent need here on Earth. I know you know this discussion, but this is very predominant, very relevant in a Danish context. But I also think in a German context, which just has elections, focusing very much on green agenda. So I think this question is quite universal, certainly in Europe. So how do you bridge, I would not say the gap, but how do you make a bridge between the Danish space strategy, which is very green and trying to focusing on meeting this climate target of 70% in 30 and other green objectives, and the interests and the prospect of going into space and doing space exploration? Well, one way could be to make this very easy equation, which I started with as I introduced myself, really building on the inherent target of sustainability, which is part of space exploration's DNA, you could say, and focusing in on the question, how can we use space exploration to promote new sustainable solutions here on ground, on Earth? How can startups, for instance, as they become part of the ESA incubation program, use the space infrastructure, the low Earth orbit installations, Lunar Gateway coming up soon, the Moon and Mars, where we're going in a very short time, to showcase and to develop the more sustainable technologies. We think it's possible, and we will make the case in Denmark. And here's one of the pioneers, which is the Danish joint venture between Danish Aerospace Company and Aquamarine Space Alliance. They are right now developing this water recovery unit, because as you know, water is an extremely important commodity in space, despite the fact, you have to reuse water in order to survive on the station, the space station. And so this technology is trying to develop a new standalone water recovery unit. You can recover urine and other gray water matters and turn it into drinking water. This is an example of one of the technology which is often highlighted by the director of the space exploration, ESA, David Parker. Is one of the technologies that is very could potentially be very important in space exploration, but could also, of course, be used on Earth in remote areas to recover and urine, to produce a new to solve important questions about water supplies. This is just an example. It's one of the pioneers, but, and this would be my last slide, we think that in-space manufacturing is one of the potential new sustainable technologies in space. Certainly has the potential to lower the footprint on materials used and reduce weight and waste, something that are very important parameters for anyone going to space, but it's also very, very useful on Earth. So this could be one of the key sustainable technologies in space. And I know today we have one of our new partners in our partnership, Atlant 3D Nanosystem here. And I think they represent an exciting example of one of the future, perhaps, pioneers in sustainable space exploration technologies. So I'll leave you that thought, that equation: sustainability equals in-space manufacturing, and the message that in order to go to space, we have to do it in a sustainable way, and in that way, we also make a bridge between the urgent climate situation on Earth and the needs we have to develop new technologies in order to go to Moon and Mars. Thank you.
All right. Thank you so much, Peter, for that very interesting presentation. And we got a deeper insight into the space strategy, but also for me, what was really interesting is how you connected to the topic of in-space manufacturing, because it's upstream or downstream. So let's get a bit more deeper into the topic. And next I have with me here in the studio, Michael Kringa. He is leading the in-space manufacturing initiative within D-Cube. D-Cube is an associated startup with ESA Big Bavaria here where we are sitting at. And yeah, I'll pass it over to Michael to tell us more of their exciting journey with the small sats, and let's go.
Well, thank you for the kind introduction, Sonali, and for the invitation. A very warm welcome to my today's presentation. Let me quickly share the slides. All right, now you should be able to see the slides. Yeah, I want to talk today about in-space manufacturing of structural elements at deployables cubed, or short D-cubed. This presentation is not so much about theoretical concepts. Moreover, it should show how we really want to work and implement in-space manufacturing for future missions. So you all know the space domain is changing dramatically from old space to new space, and in-space manufacturing will help to accelerate this transition even more. Let me briefly explain what the new space transition means. In the past, we launched single huge satellites. Now the trend is to launch hundreds of tiny satellites. Also, the speed from the first draft of a space project to the implementation is reducing from sometimes decades to weeks. And therefore, the costs are getting reduced a lot, also because we use components off the shelf instead of custom designed components, and also because the projects are no longer carried out by space agencies, but also by companies like, for example, also startups. But there's still another limiting factor which keeps the costs of today's space missions still high. It's the rocket launch itself. In rockets, you all know that the size and weight you can launch is limited and very costly. Only around 5% of the total mass of the rocket is for the payload, and it should be used as efficient as possible. For this, D-Cube is recently working on deployable structures for satellites to decrease the weight and volume of the launch, and therefore to decrease the overall costs of the space missions. For those who don't know what deployable structures are folded, highly integrated mechanical structures, for example, for stowing communication antennas, solar arrays, or drag sails on a very small footprint during the rocket launch. Yes, from the motivation to reduce these overall costs, D-Cube was founded. D-Cube has started with their micro actuators to hold down and release mechanisms for CubeSats and smallsat applications. We have here a pin puller, which, like the name says, pull a metal pin to release, for example, a spring-loaded mechanism. On the other hand, we have the release nut, which releases a nut, which also can be used to release a spring-loaded mechanism, for example. We offer different sizes of these actuators for different actuation forces. On the other hand, we also work on deployables. We have our deployable space selfie stick, which is a 1 meter long deployable boom, with which you can take a photo of the spacecraft from the outside, and the space selfie stick fits into a 0.4 unit CubeSat. Yeah, and we have also, where we're working right now, the PowerCube project, where we want to have a deployable solar array, which should generate 100 watts of power, and it's a origami design and should also fit in the end in a 1-unit CubeSat. So deployables are great and a great way to improve packaging for launch and enable new possibilities, but there are still some limitations in terms of maximum achievable size due to the launch loads, and there are still the launch loads are still acting on the deployables, and they are fairly complex. That's why we're also working on in-space manufacturing. Since in-space manufacturing enables new possibilities in terms of larger structures, we also want to use in-space manufacturing, especially with our deployables. So we want to merge the best out of both worlds. And as you can see here in the picture already, we are not starting from scratch. And we have in total 3 employees who worked already on hands-on student, ESA, and DLR projects during their master studies at the Munich University of Applied Sciences. But I tell you more later on this. So let's focus more on the technology standpoint, on what are we working right now. So we are working right now on a 3D printing method to create tube-shaped booms directly in space. With this, we want to be able to create booms that are several meters long. Previously, we only could create photopolymer rods, like you can see in the picture, but these rods are a lot weaker compared to tube-shaped booms. With these booms, we want to use them for our deployable applications. So the printing unit should be small enough to fit into CubeSats. And so we're thinking about to use them for deploying our space selfie stick, for example, deploying sensitive instruments or flexible solar arrays out of our spacecraft using this in-space manufacturing method. The process we develop has a low volume and weight requirement, as well as a low amount of moving parts. So the goal is to keep the overall complexity low. Otherwise, yeah, you know, it will be hard to convince customers to use in-space manufacturing, at least at the standpoint we have right now. In addition, the concept is very scalable. If you want to have a longer boom, for example, you simply add more space in your resin container. Yeah, and we want to achieve this goal by using photopolymers, and in the near future, we also want to reinforce them with carbon fibers to increase the mechanical strength. And here you can already see a picture of our photopolymer curing section with which we test the concept right now. We want to be able to print a 2 meters long boom out of a 1 meter CubeSat. But please understand that I cannot go so much into detail at the moment. Yes, with this slide, I want to show you on what we are building upon. As I was already mentioned at my introduction, that I was already working on the topic during my studies at the University of Applied Sciences of Munich. We came up to in-space manufacturing due to our professor at that time, who encouraged us to apply for the FlyOTesis 2020 campaign, which is an ESA student program. With this program, you get the opportunity to fly experiments during a ESA parabolic flight campaign on a Airbus A310. So we formed as a student team and applied with our photopolymer printing process and got selected. You can see us quite proud in front of the plane. Well, our topic was to investigate how the printing of structures with photopolymers behaves in 0G. We had major concerns before the flights because of the liquid resin we wanted to use for this, but it stated out that the behavior of the photopolymer in 0G is really similar to that on Earth. It was even easier to handle. So the overall process worked very well. And besides of this, we could gain a lot of data about the process. So you can see in the picture that we were able to create a little truss structure during 0G. With this good results in the back, we got invited to another ESA parabolic flight campaign. This time it was a partial G campaign with parabolas of 0G, lunar G, and Martian G. So we're also able to get data with between 0G and 1G. So in total, we had 184 parabolas for experiments. So I can tell you, we have now some experience with curing photopolymers in changed gravitational environments. Yes, the Munich University of Applied Sciences is very active on the topic of in-space manufacturing. We had during that time also a partner team, which is still active. It's the so-called AMOS Rexus team. They do investigation of photopolymer printing during the microgravity phase on a sounding rocket. And the flight got now several times postponed due to Corona. The next launch date is now on March 22 for this. And with this flight, we want to be able to get data of the curing behavior of our resin in 0G, but not only in 0G, but also in combination with vacuum, which is pretty nice. So the team leader of the AMOS Rexus team is also one of the co-founders of D-Cubed. So you can see we got a quite high competence out of engineers and researchers where we can build upon. So what are our next steps? We got a co-founded PhD between the ESA and the Munich University of Applied Sciences and D-Cubed in combination. In this case, I will be the PhD candidate, and it will start already in December. Goal is a research on concepts and applications for photopolymer space structures, and also to find a break even between deployables and ISM structures. So we have also applied for the ESA Star Tiger program. And with this project, we also want to do with the Munich University of Applied Sciences. It's a sprint project where we have 6 months of time. You come with a highly motivated interdisciplinary team and get funded by ESA. There we want to make a printing unit that creates carbon fiber trusses, also in combination with photopolymers again. It's a bit of a different approach, which I showed you before, but it's a bit more complex. We are looking forward to this right now. We got already quite far in the selection process, and at the moment we are under the 3 best proposals, so we are very excited for this. And yes, besides of all of this, we are constantly keep our eyes open where we could use in-space manufacturing for projects. We keep on working on our existing ideas. And of course, we are also searching for options to collaborate, development partners, application options, customers. So we came now to the end of my presentation. Thank you very much for your attention. And I'm looking forward to your question afterwards.
All right. Thank you so much for their super interesting presentation. But didn't it get too technical too soon? How about we take a step back and because I see we have a bunch of participants here who may or may not be experts in space manufacturing or in-orbit manufacturing. Next up, we have exactly for that purpose, Arvind Ravichandran, who is joining us from France, Toulouse. And he's an independent consultant, writer, podcaster at TerraWatch Space. And he's also alongside the director of space strategy at tomorrow.io. So Arvind, the stage is yours.
Brilliant. Hi, can you hear me? I hope you can hear me. Brilliant. Okay, thank you. I'm sorry I'm not able to switch on my video because I'm actually at a ESA center in Italy here, attending another conference. So unfortunately, my internet does not work very well on the laptop. So thankfully, my slides are over there and I can get started. So thanks for the introduction there, Sonali. And yeah, thanks for inviting me to be part of this panel. So yeah, quick introduction. My name is Arvind. I'm an independent consultant at TerraWatch Space. I also write a newsletter for the space industry. I also have a podcast on the space industry. The thing that I found is, just to go on my background as well, I come from the world of software. So for the first 5 years of my career, I worked in software. And then I moved into the space industry about 5 years ago. And, you know, it's been a journey. There's been a lot of learning of how things work, what are the different domains of space. And in the last few years, of course, in-space manufacturing has, you know, caught the attention of everybody. And I've been involved in my work as an independent consultant. You know, I've been involved in a lot of due diligence for investors, work with space agencies. For instance, I worked ESA on a few other projects. I also recently, actually this year, worked on a due diligence for an investor who was not from the space industry and who wanted to understand the potential of in-space manufacturing. So as Sonali pointed out, perhaps the talk was technical for maybe a few of you. So I wanted to take a step back and, you know, ask ourselves, what does in-space manufacturing actually mean? And that's kind of what I want to explore in this presentation. It's, you know, it is not going to contain any market figures, because, you know, I'm still yet to find a good market figure of what in-space manufacturing actually means, because there are segments of in-space manufacturing, you know, that have been getting popular, you know, like deployable structures, like on-orbit refueling. And then there's some work going on with respect to, you know, how you can use that and transition to a space mining economy. So there's a lot of work going on. So I want to take a step back and use this presentation to just create some thoughts, and, you know, hopefully we can continue that over the panel and the Q&A. Next slide, please. So what is in-space manufacturing? So how do you think we can look at the industry? Because in-space manufacturing is such an umbrella term. And for me, it's similar to the space industry, and it's a whole new industry itself, right? In-space manufacturing can be for the space industry. It can be for pharmaceuticals. It can be for optic fiber cables. So would you call that telecommunications? You know, what industry would you even place in-space manufacturing in? And I hope that, you know, during the course of the presentation, we're going to hear from a few entrepreneurs and folks who work in companies that are attempting to do that. So it's interesting to figure out how to even communicate that outside. You know, there's a lot of interest going on within the space industry about, you know, different domains of space, and in-space manufacturing being one. What is it going to be even used for? What is the market size of it? You know, is it in the billions? Is it in the millions? How do you even start to define that? Next slide, please. So the thing that has caught the attention of everybody is in-orbit servicing. You know, there's going to be Daniel Faber from Orbit Fab, who's going to come and talk, I think, 3 or 4 presentations later. There are also, you know, companies that have demonstrated in-orbit servicing for refueling purposes, and also for space traffic management and space debris management purposes. So in-orbit servicing is, you know, one aspect of the whole in space manufacturing market. Although it has nothing to do with manufacturing in space, you know, it gives us the basic infrastructure to start manufacturing in space. So it's again a very interesting space to look at. Obviously, there's, you know, what I call the nuts and bolts of the industry, and I call these the boring problems. And all the boring problems will also fit into this industry, because what kind of interface would you use, on space? And, Orbit Fab is working on that. And there are also a bunch of companies who are working on that. Those are all, boring problems. I call that boring because nobody wants to work on them. It's the nuts and bolts of an industry. Like, do we even know where the nuts and bolts of a car are manufactured today? Do we know the nuts and bolts of, big industrial plants? How do they work? How do they fuel? What fuel do they use? These are all things that we don't talk about or even think about when we think of industries. But in space, these are all going to become relevant because essentially we're trying to create an industry in space, in a different environment. Technical challenges. I don't want to get into that, but there are a bunch of technical challenges also to keep into account. So all of this fits into the in-orbit servicing industry, at least in my opinion. I'd like to hear from folks coming up later and also in the panel discussion and the Q&A about how we can start, communicating it. In-orbit servicing, of course, has caught the attention of everybody, and that's what people have been talking about. Next slide, please. And of course, there are people, who are, selling the vision that we are going to become an in-orbit manufacturing economy. We're going to start mining and, start processing things in space, either bringing it down to Earth or maybe, take it to Mars or to the moon. And those are all, very, very big picture questions, which are very interesting to ask. But then, the things that an investor asks me when he or she comes for due diligence to me are, what is the market size? Who are the players? What is the technical risk? What does the financial risk look like? And, how does the team look like? Those are all things that they care about. And it's essential that, when we're trying to sell the big picture to either to investors, to space agencies, it's easier because they are kind of within what I call the space bubble, because they understand it. They only, they would want to know more on the technological side of it. But then the investors, it's completely opposite, right? And there's been, reputation within the space industry that we focus a lot on the technology and not so much on the applications. And in-space manufacturing is, one example of where the focus needs to be on the applications. Next slide, please. So that's the question that I want to ask. So how do we define the market? Apologies if you hear something, there's a helicopter going upstairs above me, sorry. So how do we define the market? That's the first question that I asked myself when I was doing this due diligence for this investor, who was basically looking into, I believe it was the first funding round or the second funding round of a startup. And honestly, there has not been a lot of work done, because in my work in communicating about what the space industry does, even I hadn't focused a lot on the in-space manufacturing segment until I got into this assignment for the investor. So that's the first question that I asked myself. How do I define the market? Do I start from the space segment? Do I start from, because the investor wanted to get a big picture view of, okay, what is the total market of in-space manufacturing? Is it a market that we need to enter or not? Because, they are not a space investor. They wanted to get the full big picture view of what this market actually means. Is it a market in the millions? Is it a market in the billions? And this is something that I had to develop for the course of, for the due diligence that I did for the investor. And another question that I keep asking myself is, we're probably, reaching a point where we are starting to demonstrate in space manufacturing. We saw Varda Space, that's another startup from the US, that are going to launch in early 2023, if I'm not mistaken, to demonstrate in orbit in space manufacturing and, bring materials back down to Earth. So it's interesting to see how they demonstrate that and, what implications it's going to have on the overall in-space manufacturing market. But I keep asking myself, how do I communicate this to folks outside the space bubble? Because they're all, essentially the space industry has started commercializing only 5, maybe you can say 10, but that's it. People are just getting into the understanding of what the space industry actually means. And, to be very honest, it is kind of, overwhelming to understand, because, if you step back, there is observation, there's communication, there's launchers and satellites and space tourism, which has been in the news, a lot more than necessary, if you might ask my opinion. But there are other areas of space as well that we need to communicate. And on all of that, within that, there is in-space manufacturing. So how do we start to think about it? Next slide, please. So this is just the last slide, and I want to spend quite some time, thinking about it and, explaining how I'm thinking about it. So essentially, what I've discovered is that people in the space industry start, talking about in-space manufacturing, as I've heard them speak about, you do in-space manufacturing to develop the economy in space. So you basically do something for space. So you go up and you stay there, and essentially, continue doing activities that are going to be good for the overall space economy. So, very long-term vision. And I believe a lot of people in the panel share that long-term vision. And then there's the, I don't want to call it short-term vision, but then the ones that are focusing on what we can do for Earth within space manufacturing. And this is kind of how I've seen a lot of folks in the industry communicate. And I was, I wanted to propose if an alternative narrative could work. That's just something that I was communicating it to the investor, saying, in-space manufacturing has actually a lot of applications across industries. So I split that into three: space transformation, industrial transformation, and sustainable transformation. So essentially, you can argue that in-space manufacturing has, implications across industries because, from manufacturing cables to, medicines to creating space stations and space habitats and, fueling in space, the applications are enormous, right? So the way I communicated it to the investor, which, kind of made sense to the investor, and we arrived at, some way to define the market, was using this. And of course, within the three, you need to include the space infrastructure as well, deployable structures like G-Qubit talked about recently, and probably what Ruad is going to speak about next. And others are going to probably touch on this subject as well, because without the infrastructure part, you can't get into the actual applications. There was talk about how in-space manufacturing can help in the whole sustainability talk, and how we can reduce what we're trying to do on Earth in terms of emissions, or anything that we're doing to the environment. How can we move that to space? That is kind of the vision of Jeff Bezos and what Blue Origin, I think, is attempting to do. There's that, and then there's the industrial transformation. You can argue that industries across around the world will have impacts. You're going to have implications on mining, especially if you're getting into exploration and asteroid mining, especially with the moon, the interest on the moon. And of course, the interest with pharmaceutical has always been there. There have been some demonstration missions in the ISS with producing new drugs. So you can even create a narrative around in-space manufacturing for pharmaceuticals, in-space manufacturing for mining, in-space manufacturing for utilities or telecommunications, if you're talking about optic fiber cables again. So, essentially, you can create a whole narrative around each of these sub-industries. And, that's something that, I hope that we start doing more, because there's the space segment, which is, again, very important, because that's where the technological challenge is being solved. But then it's also, I think, equally important to focus on the end user and the application segment as well. And, come back from there about how in-space manufacturing can have an impact on a specific industry. So that's something that we did together with the investor. And, I'm glad to say I can't reveal the name of the investor or the company, but they went ahead and did the investment because they found the value proposition to be fascinating, that whatever this company was developing can have an impact across sectors. So, that's something that we need to sell more and talk about more. And I hope that we can have a discussion about that during this session and, in the forthcoming months and years as well, as in space manufacturing, the industry evolves a lot. And yeah, that's basically what I wanted to talk about now. That's basically the presentation that I had. Thank you.
So yeah, thanks a lot, Arvind, for touching. You touched quite a few important topics there, and thank you for the generic explanation for the newbies around here like me. And you touched about the space bubble and then changing the narrative, and we'll pick up those trends when we move on to the discussion part. But you also mentioned structures and why they are so important before we even start talking about in space manufacturing, right? So let me just bring it up to next speaker that we have on board. We have Christian Melzer from RUAG Space. It's a Swiss company, but Christian here is based in Germany. And he's been sort of the key figure in the additive manufacturing initiative within RUAG Space. And at the moment, he's leading the mechanism programs for satellites. So Christian, please shed some light.
Thank you very much for the kind introduction and for having me here. So please give me the chance to share my presentation here. Okay, so first of all, Sonali, can you see my presentation now?
Yes.
Okay, very good. Okay, so the topic I want to talk about today is the optimized advanced manufacturing for space products, status and outlook. Yeah, my agenda for today is to give a brief introduction, especially about Workspace, what we're doing, what is the daily business, and going into the motivation for us to use advanced manufacturing for space parts. Also, what is at Workspace understand as advanced manufacturing. Of course, I want to show you some examples of RUAG use cases we developed here. Oh, sorry. And at the end, I will give a short outlook and a vision what we see for the next years in the space business. Yeah, Workspace is one of the leading supplier for space hardware in Europe. So I give you here a short overview about the typical applications we develop and we also deliver to our customers. This is concentrated into the product group spacecraft. We also have a big business in the launcher segment, but I will concentrate a bit more on the satellite. Here we are doing satellite structures. This is already mentioned by Sonali. That's the core business for also our site in Zurich. We also invest a lot in satellite mechanisms development, thermal systems as well. As you know, we need or we have a really harsh environment in space. For that, it's needed to have a thermal system to guarantee the performance of our payloads. We also have a slip rings business. This is used for components as, for example, potentiometer to detect rotations for space applications. But we also support our big customers and the large system integrators with mechanical ground support equipment at their business. Yeah, to come to our motivation. So I would say a space project is not too much away from a regular business in regular industries. We also have to focus at first on performance, and for us also in project management, it's important to have a really detailed view on the costs, the lead times, and of course also the mass. We also had in the presentation before a number for cost per kilogram. So what I want to highlight here, some official source about the payload costs nowadays and also in the past for the payload per kilogram. So what I highlighted here is the 1.5 or $1,500 per kilogram. That's really the lowest possible costs we have at the moment. That could be achieved with the SpaceX Falcon Heavy. That's a really big one, and that's not really representative. And if you look more on the top yellow points here, we are in the range of the 30K, which was already addressed in one of the presentations before. Yeah, to explain a bit more in detail. So for us, it's really essential to allow the performance which is specified. That's really important. Mostly we have really costly missions. So for that, it's a really big fail if the mission goal cannot be achieved. So as you also can imagine, maintenance is mostly not possible or not possible under normal circumstances. Of course, we also have a field in the for example, ISS business. For that, of course, it is possible, but mainly if there's a big failure in the system, the mission goal is not achieved for that. Yeah, we discussed also the mass. That's Even if we have nowadays lower cost per kilogram for the payload, the mass is always critical, and to have the highest benefit, we have to also reduce the mass. So the number or the high complexity of the parts results also in a long lead time, and of course also in high costs. As you can imagine, also especially for complex payload parts, we have a high number of parts in use, and for that it's also a high effort in assembling and integration. Yeah, the situation at the moment is as well that different functions has to be implemented by also separate parts. This is resulting out of the conventional manufacturing methods, which are known and which are established over years and decades. But nowadays we have much more potential to use also so-called advanced manufacturing methods to have also a function integrated design. And last but not least, we also have to focus on the lead time. And yeah, as you know, if you have one important part crashing at the end of a project, then of course the project schedule crashes as well, and we are gaining as well for new opportunities to also relax the project schedule. Yeah, this looks like this. We developed over the last years end-to-end engineering process, and also I want to show here some benefits out of this. One of the main aspects which I raised at the in the last bullet of my slide before is of course the shorter development time for that. So it's not needed to have all full cycles like we know it from the times before. We can now really have a system optimization and a functions integration by having much more design freedom than, for example, just drilled parts or so. We can also improve part count consolidation. We have mass serving performance optimization, and of course also by this cost and lead time reduction. You know, we are talking here mostly by powder bed processes, by additive manufacturing, and for that we can drastically reduce lead times. For example, it's possible to reduce lead times to 10% of the conventional parts which are in use. One point which is also very important for us is flexibility and scalability. That means if we fulfilled a qualification of subsystem of a part and we can use synergies from an older project, scalability is a big topic for us. So the complete development chain and the qualification chain, which could be drastic in space business, could be reduced as well, so that for the lead time, another reduction possibility is identified here. Yeah, and what is also important, and I will also show you a bit more in detail the process control and the understanding of the overall chain. But this is just an introduction into the topic. And now I want to show you what is advanced manufacturing at RUAG and a bit the storyline behind that. Yeah, we started in 2014 from materials and process side. We had our first investigations of the use of additive manufacturing by powder bed processes. Out of this, we started to think about first optimized designs for parts for use in space. Out of this, we also developed a first qualification approach for additive manufactured parts in space. So just to make a remark here, so we have in form of ECSS a standard for space development, and since last year it was not covered at complete manufacturing technology by additive manufacturing, and this was so to say a first internal step to cover this by a standard approach. Sorry. In 2016, we fulfilled successfully the qualification program for an additive manufactured start tracker bracket. In 2017, there was a successful development of a lunar lander structure. In 2018, in January, the Star Tracker bracket was successfully launched, and so it resulted in the first flight heritage of an advanced manufactured metallic part. And out of this, RUAG had also the possibility to work together with an expert team at Aztec to develop SOP approach for the qualification of additive manufacturing, additive manufactured hardware for use in space. And the lunar lander shown or developed in 2017 was successful launched, not successful landed, but successful launched in February 2019. Later on, we also looked in the polymer direction, and for that, we could also successful launch polymer venting ports for the final stage fairing of a rocket. And as I already mentioned before, in 2020, the first draft was published of the ECSS, so the standard, especially for the implementation of additive manufactured parts for space. So what I'm presented here was mainly driven by the agency business. We also had the topic today talk about a commercial business, to talk about telecommunication satellites. For that, it's much more different. So it depends, of course, of the customer and also of the budget of the project. If there's a need, or if there, let's say, if there is a possibility also to have for a small budget the implementation of additive manufactured parts. And for that we can let's say show a wide heritage on that parts, and had also some success in the past. Now I want to give you shortly 3 examples of additive manufactured parts in RUAG space, what we are doing, completely different topics. I want to start with some structural elements. That's, I think, well known to have bionic structures which are replace old parts, which you can see on the left side, manufactured by conventional methods. To show you just quick the benefits out of this. So first of all, we could reduce the overall number of parts from 21 to 1. So that's a really, really big advantage. A mass reduction of 57%, increased natural eigenfrequency by 103%, an overall cost reduction of at least 50%, and last but not least, also reduced lead time by up to 70%. But as I said, this was just one assembly, and the potential of a large assembly could be, of course, much higher then. Another topic which is also quite big in our focus is the use of additive manufacturing for flexible hinges and compliant mechanism. Just to show you in a short view the need of flexible hinges and also of compliant mechanisms, especially for space applications. We had already the topic today that a mechanism is essential for a mission and also for a spacecraft, for a satellite to deploy, to also to point, to position, and also to calibrate systems. So one a well-known example nowadays, Hubble is just before launch. Just for the deployment of the Hubble telescope, there is the use of 120 mechanism. So for that, you can imagine a reduction on mass and money. That's really, really important for that. So the big advantage of those compliant mechanisms, especially for Earth observation missions, is here to have high accuracy, to have no friction forces. This is also focusing a bit in the cleanliness topic. And so on the right side, you can see some examples also from former GSTP activities, developments together with ESA. On the right side, a picture of a gearbox, a monolithic gearbox. It was manufactured like this. That's just one part. It has a reduction of 8 to 1. It's a rotational gearbox out of titanium alloy. So the overall size of that is around about 70 millimeters. for imagination. So on the left side, we have a design, an early stage design of a pointing mechanism, a 2-axis pointing mechanism, where you can put, for example, a kind of mirror inside and rotate it around the 2 axes here. Yeah, as I already mentioned, the use of additive manufacturing, especially for compliant mechanisms, could lead to completely new performant kinematic topologies. That's really important. We have, as I already mentioned in the structural topic, we have a really good modularity and a high scalability. There's just a border of the machine so far. Yeah, but we also aware of a certain risk and limitations of the process. For example, blade thickness is one topic. To have the flexure elements, as you can see, for example, here we have dependent from the material and also from the process, just yeah, a limitation of the blade thickness. And not to forget the surface roughness, which has huge impacts on the fatigue strength. So, for example, we are talking about 100,000 to 10 million cycles for that. So we have to guarantee also a certain fatigue strength to allow the performance of the mechanism. To show you just the status on that, some pictures from the titanium project here. We also had a lot of investigations of surface post-processing methods, especially for such compliant mechanisms, to investigate in different post-processing methods, which are not like a drilling, for example. It's a very automatic process which could be done without a big effort. And as you can see here, we received good results out of this and have, yeah, let's say we see a lot of potential for space mechanisms to use the additive manufacturing. But additionally to this, we also looked in completely other directions. So as I already mentioned, for mechanisms, it's important to, yeah, or let's say one of the big characteristic of a mechanism, something is moving. That's important, and for that we also get very deep in contact with sensoric, with actuation, and we also looked for additional or new novel materials which could lead to benefits. Here we have an example of an additive manufactured ceramic package for a magnetoresistive sensor. So the biggest advantage here is that we have a really lightweight design, that the ceramic could be manufactured really precise. We have here aluminum oxide ceramic used. This is lithography based manufactured, and we could use the material in a very low mass in radiation hard environment. Yeah, the benefit of this product here, this is used by, let's say, different processes, different additive manufacturing processes, and manufactured in a complete hybrid end-to-end process. Yeah, and to summarize this, one of the biggest vision of us here is, yeah, to innovate space, and of course to use the high technical and the scientific demands in space business to accelerate as well the development and establishment of the advanced manufacturing technologies. Even if we didn't discuss the in-space manufacturing, first of all, we have to establish a certain quality for the advanced manufacturing technologies on ground, and then we can not say easily, but we can adapt this and implement this for in-space manufacturing. And I'm really strongly believe that we in some years will have no spacecraft at all with without one part produced not by additive manufacturing. Yeah, thank you very much for your attention, for having me here, and I'm awaiting your questions at the end of the talk.
Thanks a lot, Christian. That was super interesting. You also touched on some really important topics here. And the question really is it manufacturing for space? It is manufacturing in space. What does actually manufacturing in space look like? So next up, we have Ali Mohammadi, who's an expert for transfer design and manufacturing and an expert in energy efficient machines. And he's going to give us a basic understanding of what does it even mean to manufacture in space, to, for instance, manufacture on the surface of Moon. So Ali has experiences, he's a DTU alumni, and he has experience at the ETH Zurich. And yeah, he's through his company for Industry 4.0, he's supporting the industry with energy efficient manufacturing solution. So Ali, I hand it over to you.
Thank you, Sonali, for introduction. So I'm Ali. I want to talk about energy management for 3D printing in space. I use the term 3D printing here as interchangeable with additive manufacturing, but in reality, it is not. Just to make it simple, I use the 3D printer or additive manufacturing. For the 3D printing will play an important role in future space exploration. They already tested the 3D printing with the lunar regolith on Earth. They use only the energy from the sun. They melted the powder and then solidify, and finally they get a good structure. Let's have an example. We consider that we want to do the 3D printing on Moon. The temperature, average temperature during the day on Moon is around 100 degrees Celsius. And at night, it will reach to the minus 180 degrees Celsius. When we do the additive manufacturing on Earth, we start from 20 degrees Celsius. We heat it up, put the energy to the material, go to, for example, to 2000 degrees Celsius. Then we get the energy and it's cooled down in the room temperature, and it's back to the 20 degree. And let's compare with the Moon. During the day in a Moon, we have a temperature of 100 degrees Celsius. So it's easier and it needs less energy to reach to the 2000 degrees Celsius. And also for solidify, it needs less energy. So with this figure, we can say that 3D printing or additive manufacturing in space needs less energy and it is more energy efficient. But there is temperature variation on Moon. 1 day on Moon is almost 1 month on Earth. And during 1 month on Earth, the temperature variation is around, let's say, 20 degrees. For example, in October, the temperature minimum is 5 and the maximum is 25. So it's only 20 degrees. But on Moon, it can reach to almost 300 degrees Celsius. And let's say, because the temperature on Moon also depends on the surface of the Moon, so it can be some realistic to say that temperature variation is around 100 degrees Celsius on Moon. So even with the 100 degree temperature variation, it needs a lot of energy to make a controlled environment for the manufacturing. So it makes some challenges for manufacturing. For example, 3D printing of a colony. They start during the day when the temperature is very good, 100 degree, but it will not finish, and the last part will be finished at minus 100 degree, which is not efficient at all, and maybe the lack of energy to finish the colony. And the other problem, the microstructure is different. One of them is solidify at 100, another layer is 800, and these two doesn't match, and the colony will collapse. Another challenge is for 3D printing of a device. Is it performed in a controlled environment or non-controlled environment? And is it possible to stop and start again the 3D printing? Because maybe the temperature, when they start, the temperature is quite good, but when during the night they don't have energy, they have to stop the process in the middle. there are some solutions. For example, they can install the 3D printer on a rover, and it tracks the temperature and goes by where the temperature is 20 degrees. So it has more good condition for environment to have around 20, 40 degrees Celsius. So it doesn't need that much control environment. Another thing can be in they isolated the 3D printer, put it in a colony, and then the 3D printing is independent of the outside temperature. Also for the printing of a colony, it can be combined with other methods. For example, drilling, ultrasonic drilling, which previously also tested. They can use the ultrasonic drilling in a rock surface and pull up some column of rock. And then they use this additive manufacturing such like act as a welding and fill the gap between each rock. So they can, it's much faster to them to make this colony and make the initial base for in a space manufacturing. So at the 4i4, which represent for Industry 4.0, we can do the energy calculation for space manufacturing. We have experience in machining and also ultrasonic devices. We have detailed knowledge about efficient programming for machining. For example, a CNC machine or a 3D printer has a cross table. If X and Y, one of them is on top of the other. If we program somehow to use the top table, we need less energy for manufacturing. And this can be, this also needs a motor with less power demand. Also, the microstructure is very important because it's temperature variation. They have different solidification temperature. So we have knowledge about the microstructure. We also equip with an energy efficient CNC machine. This idea about the table and programming is implemented in this machine. And we want to supply our customer with product friendly, eco-friendly products. We can also do the assessment of the ISO standard for energy efficient of the machine tools. And at the end, I have to say that I have to flash back to what Peter and Arvin says about the sustainable product is connected to the space manufacturing. And I think the aim right now in the manufacturing is to produce fast and cheap, but it should change to more sustainable product in order to be successful in future space manufacturing. And that's all for me. And thank you very much.
All right, thanks a lot, Ali. We will come back to those questions of sustainability and energy efficiency for manufacturing in space. Right now, we are running 10 minutes, roughly 10 minutes late on time, but we had some buffer time exactly for seeing this. So let's just take a 10-minute break, and then we come back for some further exciting presentations, both from Maxim and Daniel. And Daniel is actually joining us. Thank you, Daniel, for getting up so early and joining us from Silicon Valley. So guys, stay tuned, and we'll be back in 10 minutes. Hello, guys. Are you here with me and with us for the webinar? I hope you were able to grab a cup of coffee or tea, or if it's too late, something stronger. And now you're ready to move on to the more interesting part of the webinar today. And next up, I have Maxim here, who's the CEO of Atlan 3D Nanosystems. He is a nanotechnology expert himself. And before putting too much words into what they're doing and who is, I'll just pass it over to Maxim. The stage is yours.
Thank you, Sonali. It's a great pleasure and honor to present what we do and how we work as a company in also space for space industry. I would probably start just with my presentation and then give more insights how the things are going on for us. Can you see my screen now? Can you confirm, please?
Yes.
Hello? Okay. I'm leading Atlant 3D Nanosystems. We started the company almost 3 years ago back in Copenhagen in Denmark. Now we have part of the team in Erlangen in Germany. We are 15 people, 10 of us full-time, mostly PhDs in different fields, microtech, chemistry, manufacturing, computer science, economics as well. So very, very broad and very diverse team, in not only in terms of expertise, but also in terms of nationalities. We almost don't have the same two people from the same country, even though we are in Denmark, which brings a lot of diversity, a lot of interesting discussions almost every day. Myself, I have a PhD in micro nanotechnology from Technical University of Denmark, and now live here for 7 years. The future in space, how we all imagine this, I think with the recent progress, companies like SpaceX and others brings a lot of opportunities that we can establish as a multiplanetary and also space manufacturing or space habitable civilization. So this brings a lot of challenges and more interesting opportunities. And these opportunities bring a lot of technologies that can be brought. So one of the technology which is critical is how to set up a space manufacturing. There are, of course, pioneers already. Like, I really like the case of Made in Space. I think they were the most prominent bringing and advertising what they do. They simply build a 3D printer that can work at micro and zero gravity, print some plastic tools. And this company was acquired also by Redwire. And Redwire is a recently listed company that actually doesn't only print some tools, but they deploy even solar cells in space, and a really, really cool company as well. What is the future for space manufacturing? This is basically the future of the whole industry. So we would need not only flights, but transport by rovers, stations, habitable, manufacturing resources, and utilities. And my focus, of course, on manufacturing. There are already several or a number of companies that present themselves as space manufacturing companies, like POC, FOMS, the most recent companies that get in more success, Varda, Made in Space, that was acquired by Redwire. And I, of course, position Atlant in this line of companies, because we do want to become not only on Earth, but in space manufacturing. What can be manufactured? Many things. The most interesting for us, particularly, it's semiconductor, optical elements, metals or compounds, solar cells, magnetic, superconductor, biocompatible materials and devices. There are companies even printing, want to print meat or other or organs. And this is, of course, very interesting, but that's something not I don't want to touch. And of course, NASA itself placing a very big effort for supporting and enabling in-space manufacturing. Now, what Atlant can do for this? So we as a company solving one of the fundamental technological challenges that exist since first micro device or even first transistor appeared. In order to make an integrated circuit on Earth, you need a very advanced infrastructure, a clean room, a lot of advanced experts, equipment. All of this is very, very complex. It brings a lot of hazards. It brings a lot of time-consuming processes and cost. we bring in basically the technology that become a platform that can combine all of these processes in one and reduce all of this complexity. And more interesting why it's related to space, because this technology can work at micro and zero gravity. So this is where we touch the space. The technology is basically here. It's a printing head that works with the gases and delivering gases to the surfaces. And when the gases delivered to the surface, we create a surface chemical reaction. So it's a dynamic chemical reactor that enables printing atomic layer. So we call it not only the platform, we call it the technology. It's atomic layer advanced manufacturing technology that enables a lot of possibilities. So this is highly scalable technology. This is a technology that can work from lab to fab or lab to space, we can call like that. And also the technology that delivers a lot of materials, high purity materials, oxide, metals, semiconductor, and they can be combined in different order. So how it works, under the nozzle, we have a jet of gases, and these gases, when they reach to the surface, they create a certain pattern. So here you could see our first historical print that we did last year. It took us 2 hours. Each letter here is uniquely printed with different thicknesses, which is not possible with other techniques with such precision. Now it takes for us even a few minutes to print. So this is a cutting edge technology that we created, and brings the disruption to several industries. Here you could see we already just a few weeks ago demonstrated silicon wafer, 4-inch wafer scalable process, so we can print on a manufacturable or industrial standard wafers. And you could see here with nanometer scale, variable thickness from rastered square to 50 nanometer, 40, 30, 20. And this is just a few examples. We can control with atomically precise layers, whatever we print, and also we interchange materials. Oh, sorry, jumping too fast. NASA is also working with this technology. This technology is called ALD, atomic layer deposition, but usually this technology is a blanket type deposition. When you have a sample and you cover everything, so you cannot get a pattern. And one of the applications where they use this technology is for micromirrors, and there are many other applications that they are looking for. So we decided why not to reach to NASA and find out how this can work. And we reached out last year, and together with NASA, don't be surprised, this is not something, this is publicly available images. And we developed a unique tool that we converted into a unit that we now ship into NASA. This is a very compact micro zero gravity unit that would allow to print atomically precise layers in selective way or with patterns in a very easy way. So the next with the tool that we built, and this is a tool that we now ship into our collaborator. And also what is unique here, we actually converting this tool into a product that can serve almost any R&D needs on Earth. So any of you, if you do material R&D, prototyping of micro nano devices, and you won't even manufacture, you can actually consider this tool for your needs, of course. The next step for us is actually to deliver this tool and test it at micro gravity with parabolic flight. This is something very interesting for us. We're now looking for opportunities to collaborate with ESA on this, the same topic, because this research and this in a project in general needs a lot of support and several years of development, even though we move quite fast. Bigger picture for us, we bring in the technology for Earth and needs. So we are serving from R&D to manufacturing, but the most interesting that our technology enables zero gravity, atomically precise microfabrication, and most interesting, we can bring this technology to create interplanetary modular atomic microfabrication systems. This opens for us a lot of opportunities, and our team is extremely motivated about this. What applications? There are a huge number of applications. This background was selected for the purpose, from materials to optics, photonics, displays, superconductors, quantum materials, energy devices like solar cell or fuel cells or super capacitors, memory, MEMS, sensor. I would just skip listing all of them. Basically, this technology enables in-space and interplanetary manufacturing. So for us, we have a goal that enabling bringing our technology to ISS. This is something that we're looking for opportunity for the next year, preferably, but you know, that could be delayed a little bit. What we can do at zero gravity on orbit. Basically, with our technology, we're enabling printing of pure semiconductor materials. And when they grow at micro and zero gravity, they have, for some materials, way better properties, crystal structures, bringing new type of encapsulation, printing of, again, solar cell batteries for some materials and for some structures. It's much easier to do this there. And also, if we want to expand our space presence, these technologies must to have some devices like micro devices for biomedical applications, for organ on chip or lab on chip. They need to be printed or done in space because of the properties of these devices. The same for superconductor or quantum materials or optical and photonic devices, where some materials like Zeblan or fluoride-based material, they have poor properties when they grown on Earth, and they have superior properties when they grown on orbit. So all of this opens a lot of opportunities. We, as a company, looking for the big future, not only orbit, but other missions. And we, of course, look how we can bring our modular concept into life. This is our dream, and enable something unique to be created in space and on the other planets. On this, I would like to thank you. That's our team. We are dreamers, we are doers, and we are looking into the future with the bright ideas that we want to implement, and we're looking for partners. For you, how to reach NASA, this is a very simple recipe. Just write on LinkedIn. Of course, I don't show the name, and people usually reply. We actually got, we were quite surprised, but you know, this is how we settle our first project with NASA. We're now creating a t-shirts, so 3D printing in general, very cool technology or set of technologies. We belong to partially to that. And if you want to do something in space, I think it should be 3D printed. Thank you very much. Please let me know if you have some questions.
Thanks a lot, Maxim. Super interesting. Again, I will come back to some of the strands later on how your technology is unique and why we should 3D print and why not take stuff into space. But before we jump on to the discussion, we have the last presentation for the day, last but not the least. Daniel, are you with us? I just need a wave from you. Yes, you're here. Perfect. All right. So guys, ladies and gentlemen, we have our Silicon Valley presenter here, Daniel Faber. He's the CEO of Orbit Fab. He will tell you what fabulous things they are doing within their company, but a little bit about him. He's, for over 2 decades, he's been driving sort of the space economy in the Silicon Valley and revolutionizing the way the industry views water-based satellite propulsion systems. So before putting too much terminologies and keywords, I'll just hand it over to Daniel.
Thanks very much, and I'll share a screen here as well. Just check that that's working.
Yes, we can see.
Excellent, great. Thank you. So yeah, I'll be talking today about Orbit Fab. Our tagline is gas stations in space, or petrol stations in space. That's really what Orbit Fab is doing. My background in deep space industries, where we were an asteroid mining company in name, we were developing small thrusters in practice. That was the technology that was ultimately sold to Bradford in the Netherlands. So that became part of a European company when it was acquired. But the reason behind doing Orbit Fab, really what we're trying to do here is to grow a bustling in-space economy that can support humans living and working in space, that can support permanent jobs in space. And for that economy to bustle, we really need fuel. So Orbit Fab is, in its essence, really going to become a petrochemicals company. That is where we are looking. But right now, there's no bustling in-space economy. There's no real bustle at all. We're in this paradigm where we don't reuse assets. So if you look at similar assets on Earth, airplanes, they cost a couple of $100 million. If you were to fly across the Atlantic, say carrying cargo or people, you could make some hundreds of thousands of dollars of revenue. That doesn't pay for a $200 million plane, and it wouldn't make any sense if you had to throw that away. But over 15, 20 years life, you can make billions of dollars out of that asset. So that makes obvious sense. Cars, we refuel them once a week. Similarly, trucks and cargo vehicles and things, 750 up to thousands of refills. We get a lot of use out of these assets. Launch vehicles are now in this paradigm as well. Thanks to SpaceX, which has now done 10 refills of its most used booster, we have reusable rockets. This is really in the early prototyping stage, right? It's only now 5 years since we've started landing rockets back and refilling them. That is ultimately going to get to hundreds and then thousands of refills and reuses. But in contrast, satellites, we use them once, we throw them away, and they're done. That's it. Despite the fact that of the assets on this page, satellites are sometimes the most valuable. They can cost billions of dollars. And if you can't control them, you can't keep them in place, you can't coordinate their activities, they'll drift, they'll possibly collide. This is a real serious problem. So once they're low on fuel, we use a lot of fuel just to get them out of orbit, and really we throw them away, quite literally. That's the paradigm we're in right now, and everybody designs around this paradigm because that's what they think it always has to be. And of course, that's flat wrong. But let's look at some of the costs of doing this. Every year we throw out good satellites that at the end of their life, be that 5, 10, or 15 years that they were designed for, when they run out of fuel. Most of these spacecraft have perfectly functioning electronics, and they have customers. So the big geostationary satellites, you're throwing away $20 million of revenue on every satellite. And there are dozens of satellites every year. This is $500 million that we throw away in opportunity just because we don't have the fuel to keep them going. There's also this satellite is an example, Express AM4. I tried to buy this in a previous company. It got put in the wrong orbit. There was a glitch in the rocket upper stage. And so a satellite that cost a few $100 million to build and launch was a complete insurance write-off. And of course, there were billions of dollars of lifetime contracts attached to that the company then lost and had to rebuild their asset and try and win that business back. So every year or two this happens. It's also about $500 million a year problem. One of the more pressing issues for society is space debris. When we look at how much equipment is being put up there and the risk of collisions, we risk having a cascade collision that's going to deny us access to space for future generations. This is a real problem, and we could solve most of this and significantly reduce the probabilities of collisions if we removed some of the more dangerous pieces of debris. But we can't do that right now because it takes so much fuel to run a garbage truck service. Otherwise, you build a shiny tow truck, you'd tow 2 or 3 pieces of debris, and then you'd throw away the tow truck and have to build and launch a completely new one. It doesn't make sense, and the business models don't close until we have fuel in orbit. And then, most exciting, a bit of a look to the future, the mega constellations that are being built by Telesat, OneWeb, SpaceX, Amazon. These constellations of tens of thousands of satellites, they're single-use satellites. They talk about having to do a technology refresh and rebuild the whole constellation after 5 years. We're talking 50,000 satellites getting replaced every 5 years. Now, I see this system as a really interesting prototype system for what's going to be the cell phone towers in space. And for cell phone towers on Earth, there are millions of them around the world. When we upgrade from 4G to 5G, for example, we put on new transponders, we might increase the power supply, but we don't pull down the tower and build a completely new tower. But that's what we're doing in space. So I fully expect that in about 10 years, we'll start building cell phone towers in space, and we'll build millions of them. There'll be 1 million cell phone towers in space, and we will upgrade the equipment regularly. We might tack on some new solar arrays, and of course we'll refuel them so that they can maintain their phase and stay in that orbit. So this is what I expect to see, and it's all got to be built on refueling. Something interesting that's happened in the last few years, they've become now the existence of tow trucks in space, of satellite servicing vehicles. So Northrop Grumman is operating in geostationary orbit, attaching and providing life extension. There are people looking at inspection of other spacecraft. There are people looking at towing spacecraft between orbits, and these systems are starting to become operational. When we formed Orbit Fab in 2018, there are 8 or 9 companies building what we call tow trucks in space. There are now over 50, they're almost 60. There's about a 500% increase in 3 years. Unfortunately, all of these tow trucks are single use because there's no fuel supply, and so we throw them away. So this paradigm shift is really, really undermined by the fact that we're stuck in this single use paradigm, even though it's trying to change it. So here's what we do, Orbit Fab. We launch at fuel, we manage logistics in orbit, and we deliver it to customers in orbit. We supply fuel in space. That's it, pretty simple. So we're providing unlimited fuel where you need it, when you need it, of the type that you need. That's the crux of what we're doing. So we're already operating in space. In 2018, founded the company. In 4.5 months, we developed these 2 payloads you can see for the International Space Station. It's about 3 gallons of water, and the one on the right, the one on the left, is an inflatable tank, which we see as critical to sort of the evolving ecosystem. Later, you'll be launching not just with an empty tank, but with a stowed tank, and then be able to fill it up from a tank that's already in orbit as we run a more efficient supply chain on the propellant. So we tested that on the space station. We actually plugged that into the space station after we were done, into their water bus, became the first private company to resupply the space station with water. So that was very successful. We learned a lot of things in that process. And so we applied those then to the things that we were developing. Here's an example of that experiment in space, looking at the residual momentum and the slosh dynamics. And it is pretty cool. So we got a lot of great data out of that. Then this year, after closing our seed round funding, we built the world's first operational propellant tanker that is now in orbit. It's a small tanker, slightly under 50 kilograms. You can see it here being deployed in space off a Falcon 9 rocket. So that's carrying high-test peroxide, which is an aggressive oxidizer and monopropellant, a great fuel for because we can produce that from in-space resources. But it's on a path where we'll be selling hydrazine and xenon, which is what people are buying now. So that's the progress we've made. But I really want to talk about manufacturing fuel in space. So I mentioned that the industry currently uses hydrazine and xenon. Those are the 2 propellants. These are not able to be manufactured in space because xenon is a noble gas and hydrazine requires nitrogen. Neither of those 2 things are found on the moon or the asteroids. And that's due to the way the solar system was formed. Those are light gases that get pushed out by the solar wind to the outer solar system. So there's a lot more of those out near Neptune, but almost none of them, except at the bottom of gravity wells like on Earth, in the inner solar system. So we're not going to be able to produce a hydrazine and xenon from asteroids or the moon. But what we can produce are hydrogen, oxygen, carbon, and things that are based on that. So we did an analysis here of different potential propellants and how to get those started. And one thing that we really try to stay away from, especially as we start to bootstrap this, is complexity. And anything that requires cryogenic or cryofuels has a very high level of complexity. There's no minimum viable product for cryogenic propellants. You need to spend hundreds of millions of dollars and build things that are, tons in total mass. So we really decided then that high-test peroxide is actually possibly the only monopropellant and oxidizer that can be made from lunar and asteroid resources. This is pretty critical. So if we want to make high-test peroxide, which hydrogen and oxygen atoms stuck together, how do we do that? We did a search for the technology, and some of this work was done under government contracts at Deep Space Industries. A lot of this has been continued here, but we realized we can definitely make this propellant, and it's going to be extremely useful for the future of space activities. So here's how to make it. You need a water harvesting system, and I'm not going into that because Orbit Fab is not an asteroid mining company. We're a petrochemicals company. So we'll take that water, we electrolyze it, put it through a proton exchange membrane, which is a lot like a a fuel cell, but rather than a fuel cell which converts the feedstock into water, this converts the feed into hydrogen peroxide. So hydrogen peroxide at 3% comes out. We put that through a concentrator and get out 90% hydrogen peroxide, which is a great rocket fuel. So this is not just concept. This has been built. We licensed some tech from Rice University. That is then at technology readiness level 6. It can produce 130 liters at 1% peroxide. That's 130 liters per hour per square meter of membrane. So scaling this tech is actually fairly simple. It's a membrane technology. We couple that with a concentrator. We only need 0.7 square meters, and we can produce 1 liter an hour of 90% peroxide, which is our design target for our demonstration system. And then we looked at energy consumption. We have an end-to-end system design. This is the stuff that we're working on. Once you're able to develop, once you're able to manufacture hydrogen peroxide, you can combine that with Sabatier type systems that can take carbon dioxide and carbon compounds and upgrade them into more complex hydrocarbons as you want. And so peroxide propane or peroxide dimethyl ether, peroxide methane, these are excellent propellant combinations. And they have specific impulses basically on par with stoichiometric oxygen and hydrogen without the need for cryogenic storage, which is absolutely critical to bootstrapping in situ resource utilization. So we have a number of missions that are planned using this. We're still working on that technology, getting it up above TRL6 through TRL7 and 8, looking at potential lunar sample return missions that can be run using a complete end-to-end in situ resource utilization cycle. There'll be a paper at the upcoming International Astronautical Congress presented by Connor Gaiman, who's done this work at OrbitFab. And so, yeah, I encourage you to watch out for that paper if you're interested in how this technology is developing. So Deep Space, OrbitFab, we do real things real fast. We've built a lot, we're testing a lot, we're flying a lot. We've announced that we're sending a tanker to geostationary orbit at the end of next year. We definitely intend to make this technology a reality, and we're doing that as quick as we can. We're looking for partners across the US and Europe that we can work with to take this from the lab bench into reality and into space. Thanks.
All right, Daniel, thank you so much for that brilliant presentation. And we are moving towards our discussion. But before we enter that, I just wanted to wrap up what we have been seeing so far, what we have been hearing so far, basically. So we had presenters from Denmark, France, Germany, and now Silicon Valley. We talked about structures, we talked about fuel, we talked about additive manufacturing. And we also touched upon energy efficiency and sustainability. So all of those topics now we're going to bundle up and relay into our discussion. For the audience, it's really important, if you're there, if you're listening in, please type in your questions into the chat function, and my colleague Malu will relay it to the speakers. Yeah, then I would just call out the names of all the panelists, and would be great to have your attention. And I'll just throw questions to you one by one. So we need Michael, Arvind, Christian, Ali, Maxim, and Daniel. Great. Looks like we have a full house. Just waiting for Christian to switch on the camera. Perfect. All right, so let's move on to the more interesting discussion part. But now, since the memory is still fresh, personally also I'm really curious. Let's begin with Daniel and OrbitFab. You have a VC-backed company, and you've received a recent investment with some of the big players in the space industry. But Munich Re, the Munich-based corporate venture arm of Munich Re Insurance, is also investing in you. So what is sort of the backstory there, and why is it interesting for European players to look at, fuel in space?
Yeah, space is it's a global industry, so so of course we haven't restricted ourselves to just things that are happening within the US border. But Munich Re actually came in and invested in our seed round, so more than a year ago now. That investment for them was strategic. They're seeing satellite servicing, the potential for manufacturing, assembly, and such things, really shifting the risk environment. And they're one of the world's biggest insurers. They're the biggest insurer of satellites and rockets. And so they want to be ahead of the curve. They want to understand new insurance products. And a lot of what we're doing with Propellant, it's bringing sort of financial concepts and practices from the oil and gas and energy industries into the space industry. So futures contracts, how to ensure those financial mechanisms and all those things, those are very important to us developing our business. So we wanted a partner that really had that insights and knew how to think about this in a financial and sort of risk-centric way. They wanted a front seat to see how the risk profiles change in the industry, to see what new insurance products are needed, to see how the consequences of failures and things are going to change. So it was a really, really natural partnership and came together very well. And they've been fantastic. They have a board seat, sit on our board with a very mature corporate venture capital arm. And so they provided a huge amount of value to us as a company.
That's really great to know. So we have speakers from Silicon Valley, but we also have the European part. For me, it's really interesting to understand how the different space industry, specifically in space manufacturing industries, are developing in both the continents. So maybe to you, Daniel and Maxim and Arvind, could you maybe one by one highlight sort of the differences that you see in the ecosystem? What are the challenges? Are they unique to those ecosystems and so on?
Yeah, I would say we just less than a year in the space application domain, so we are still exploring. So I would say my judgment is very weak here. Obviously, it would be nice to have more funding opportunities. But again, it just could be the case that, you know, because of a very short timeline, we didn't explore some of the possibilities. For example, we are quite happy with the recent feedback from the Danish space ecosystem, that we could see that in Denmark, people particularly looking for something interesting, new in the space domain, and we try to explore that.
To Daniel, then, if you could just briefly put on if you see any concrete differences in the way the industry is progressing or the outlook.
Yeah, having worked in the space industry for 25 years and worked in Europe and the US now, there are definitely some differences. The US, we see investors and entrepreneurs pushing for a lot more commercial applications and willing to get ahead of the government. In Europe, I see a lot more sort of reliance on the government to provide the vision and the direction. So there are different approaches in that. But there's definitely funding on both sides of the Atlantic, and it's possible to develop tech on both sides of the Atlantic that can make a big difference. Definitely in the US, the advantage of having such a large government customer, the US government spends more on space and is clearly becoming interested in on-orbit assembly, manufacturing, and refueling. And so that's providing some contracts and some cash flow. But Europe is not that far behind, to be honest, and I see a lot of things starting to happen there. There are big companies there that are getting very interested in it. And so yeah, I think that the ecosystems on both sides are similar, but there's a slightly different sort of fundamental approach in risk posture and who's leading and who's following.
Absolutely. Brilliant points right there, Daniel. So we see that the approaches are different. One side, and maybe the government is a sort of drawing the rule. Peter, how do you see it? How important is the role of you know, the ministries, the government to sort of design this? And the space strategy is not just one ministry, you know, it's a all hands in initiative from a couple of ministries, especially in Denmark. So how do you see it, and why is it important to drive it from a government perspective?
Well, there are fundamental differences, and I agree with Daniel that in Europe, you normally look to the government and the European Space Organization or the European Union to get guidance, and because that's where also the big investments are made. So that's a big difference. So therefore it is of importance what the European Union says, very important now. I think in the future, we will see that the European Union will become a much bigger player in space. And so we will have the agenda in space in Europe will be set by the European Union. And we will see that ESA, for instance, is becoming a natural junior partner, an enabler, so to speak. The points I made with my presentation is Denmark is, of course, a very small player, even though we have some brilliant people around here. It is that in Denmark, I think we put we put space into really into question, and I think that's important. And other countries may look to Denmark and see, well, how do they justify investments in space when the Earth is burning, so to speak? So I think Denmark, in that respect, can be a test case for how do you justify continuing investing in space. I think the Daniel's a great idea, and is to stop single use in space is a great metaphor indeed for what we should be looking for in space exploration in the future.
Thank you, Peter. You briefly also made a very, very interesting and important point there of connecting sustainability and why does it make sense to invest in space, to invest in space manufacturing. So the resource perspective, the structure perspective, how can we best utilize using our technologies, our existing technologies, or building on existing technologies, and use the resources that are there in space and create value. So now that we're talking on structures, Christian and Michael, you both sort of work with deployable structures or structures that are important to be sent out there. How do you see the development, and what are sort of the challenges to innovation that you see within companies? So DCube being a young company out of Munich, and RUAG being a giant in space. So are there any difference in challenges? Christian, please, you can go first.
Yeah, thank you. Maybe to comment a bit on the answer before. So I totally agree. I also see there are big differences between the US and the European market. So first of all, if you just look on the overall budget per year, which is spent via US government and the European Space Agency, it's completely different. And also, if you look on the big market for constellations, that's not happening in Europe, we know. And also this is my link to the small players like DCube, or let's not say the small players, but the new players. So they have a big opportunity to reach there also a market, which is I would say much more difficult in Europe to become such a heritage player. And in the US, it's much more easy. You have the possibility, even if you're a startup in Europe, to reach the market in the US, also to look for industrial funding. And I think that's quite good challenge on that. And let's say to focus on your question again. So I would say the typical deployment business, if we point on the deployments, for example, at RUAG is the bigger European Earth observation missions. So there are bigger systems, and I would say the market, which is, for example, DCube also focusing on, is constellations, to look for smaller satellites, to go for numbers. Yeah, this is the potential I see, and that's of course also quite difficult to have such an let's say with a company like RUAG to go for such a market. So I think that's a quite good potential, quite good opportunities for startups to come and to enter the business.
Michael, what are your views on this?
I can totally agree, basically, to Christian from York. The cube is more or less, focusing on CubeSats and small satellites to enable them to get bigger structures out of CubeSats and be not so much limited. So we want to enable or to make CubeSats much more efficient in the future, or SmartSats in general. Yeah, but
Do you
we don't
see?
have. Yeah.
Sorry, go on.
Yeah. Sorry. I think we don't have the possibility to come directly to such big satellites as a customer. So we need to start from smaller, with smaller stuff.
Thank you both for the interesting insights. We jumped on huge macro satellites, we jumped on micro nanosats, but what about nanotechnology and 3D printing, coming back to sort of the in-space manufacturing link here? Maxim, what makes your technology really stand out as compared to, so we have had metal additive manufacturing, polymer additive manufacturing. Why is Atlant unique, and how can it contribute in a better way to in-space?
Yeah, sure. I think Michael Kringer, right, was presenting in his slides that they did printing, right, in space with a polymer, and they can stay at zero gravity. You know, this is very unique case in case of Michael, because most of other materials with low viscosity or with lower viscosity, or when they are extrusion based or nanoparticles based, they are very difficult materials to handle in space. So it means that basically bringing a lot of manufacturing methods in space is very difficult, and this creates a big challenge. What is unique from our side, that we work with gases, and the gases, I call it, gases do not follow gravity. They follow the pressure difference and where you direct them, which means that if one has a very sophisticated gas flow control system, which we have, for example, then you can define what you can do with gases and also start creating some unique features. So this is basically a default definition of our technology. Another big benefit that we want to utilize at micro zero gravity, particularly at zero gravity, that availability of vacuum around the spaceship, because in our case, this is actually the fruitful media. We need to use vacuum for work of our system. Zero gravity brings capabilities for grown materials at such conditions that they become, let's say, if you take a fluoride-based metal fluorides, like the Zeblan material, when it's grown at zero gravity, it becomes a monocrystalline. And for example, this material is well known for just superior optical properties. So we're looking into these possibilities that when we don't have a gravity as a limiting factor, to enable creation of new materials and then as a consequence creating a new micro nano devices that will potentially change everything how we consider. Now, another aspect of space manufacturing, high precision or nanotechnology based manufacturing, a lot of on Earth nanotechnology based production or manufacturing or even R&D require very hazard materials, or gases. Even those gases are very hazard. When you work in space, these things becomes much more simpler. You can work in separate environment, a glove box or a chamber, And if something happens, you just evacuate everything. And in our case, with our technology, we have very small amounts of these materials required, so which is very sustainable for space, for an in-space use. It probably was too long answer, but I wanted to cover some few points.
No, that's perfect. Thank you, Maxim. We have a good mix of young companies. We have some established companies. We have the government perspective here. So this is how we really, ICDK really works at the within the triple helix model, working together with all of these players and also trying to build and share knowledge on this. But there's always a question of, scalability. And I think Christian in his presentation touched on that and some of the work that he's doing or they are doing within additive manufacturing. There are some problems of scalability. Could you maybe put a few more words on that, Christian?
Yeah, of course. Usually, as we already mentioned, so we are working in governmental business. That's also the experience out of the last decades for us in Europe, at least. And yeah, if you are familiar with the governmental business with ESA, so it's important to have a really high security or safety of all parts of the complete system, that it also survive the environment and to reach the mission goals. And for that, it's needed to have a full qualification of the complete satellite in before by a qualification model. That's quite sure, that's clear. And yeah, the possibility to become much more scalable with the new manufacturing process allows also to at least to implement an reduced qualification process. Every engineer who's working in space knows how much effort it is to qualify a new system, a new subsystem. It takes, in the worst case, several years, and for that, we see a big potential in having a qualified process. That means having the qualified powder, the qualified materials, and have the qualified machine, have the qualified environment for the process. And then it could be quite easy to achieve a scalable part, or to produce a scalable or a scaled upscaled model for that with a reduced qualification approach and verification approach. And that's from my perspective, this would be a big advantage for the agency business.
Thanks a lot, Christian. We in Europe love talking about digital sovereignty. We love to claim to be independent and becoming more and more independent, and space in general plays a big role in that, including, I mean, we have recently come through a crisis of silicon flakes and semiconductors. So it's really a ongoing debate throughout the industry and also within the government and policymakers. So my question to you all is, what are the key tech challenges that need to be overcome if you need to see your individual technologies moving ahead? Is it really a tech challenge, or is it a policy challenge? What is the case here? Since you are on my screen, Christian, you can go ahead first.
Yeah, I think that's a very good question. I think it also depends a bit on the location where you are. Even in the European Union, you have quite huge differences, especially if you talk about digitalization. So I think also in Germany, we have a big issue with that. And yeah, sometimes I have the imagination or the feeling that it's more a policy topic than a tech topic. So I think we are to take, let's say, advantage of all developments worldwide. So we have the possibility to implement a lot, but mostly we have to, let's say, to create the infrastructure for that in before. And that's, from my perspective, the most difficult part at the moment.
How do you see it, Peter? I will jump right to you. What do you think, or how instrumental has this debate been in you contributing to this new space strategy?
Well, we've not been focusing on high tech in this strategy. I think that's why I also had a challenge translating this earthbound terrestrial looking strategy to the outer space exploration, but it's something which we're working on. But the digitalization in that respect, in the space strategy, meant how do we use satellite program as satellites to make life easier and more efficient on Earth? How do you use the big Copernicus satellites, which ROAC contributes to make the agriculture more climate friendly and so on. So that's the digital challenge which we are focusing on, again, with a very green perspective. So we've not been focusing on the bigger supply issues. And I think someone else would have to answer that question.
Anyone else wants to take that? Otherwise, I'll move on to the Q&A. We have some questions piling up here. Any other comments to that from the speakers?
From my side?
Yeah.
I don't think it's a technical issue so far because like Made in Space showed already, they just took an FDM printer, which is the normal ordinary technique for 3D printers, made them to be able to put on the ISS, and then they showed, hey, 3D printing works on the ISS, so they just hooked up an existing printer and showed that they are able to do the same as we do on Earth, just in space. So I think what we need is a bit of a change in the mindset that we are not able to fully control everything, every system, what we want to have in space before we launched it. But in space manufacturing, if we can reduce the cost so far that it will be worth to have a bit more risk that some components fail, for example, then it could be still a nice calculation or a benefit for the whole space industry.
Thank you. Thank you, everyone, for the debate. We had some really interesting insights from funding to startup experiences. Before we just move on to the Q&A, Christian, I remember you mentioning how delightful your experience was in the parabolic flight. Maybe you can put a few words on that, and then we move on to the Q&A.
Yes, it was very good. The weightlessness feels actually like like swimming. But you realize that you cannot use your hands or feet that way you are used to do it on Earth. Otherwise, you end up flying like Superman through the aircraft cabin. But you didn't want it. So yes, it was a very impressive experience, and also not only in terms of that we could feel the microgravity, but also that we could see our in-space manufacturing process printing with our eyes. That was a really great experience we had.
So thrills and goosebumps. Thank you so much, guys, for sharing your experiences, sharing your struggles, sharing your stories. They're all beautiful, and they will all contribute to driving the space economy or in-space manufacturing forward, from technologies to policies and so on. I will just now pass it over to Malu, my colleague in Silicon Valley. I hope they're all nice and fresh. And moving on to the Q&A. So the audience, if you have any questions, please, now is the time to throw them.
And thank you, Sonali. I think we already have a few questions coming in. So let me start. It seems there's a general question on additive manufacturing from Pablo Humanes. In the case of additive manufacturing and its power to reduce material use, are the supports needed during the 3D printing process that have to be removed afterwards, possibly recycled, or is that material lost? Does anyone have anything on that question?
Well, from our side, we don't use any support. And in general, I think in space you don't need any support because since you don't have any gravity, your print does not collapse by gravity. So I think there is no need to recycle any support.
Okay, thank you. If no one else has something, let's move on to the next question. So this is for D-Cubed. Where do you see your technology in 10 years in terms of maturity and implementation?
Well, since we are a new space company, I would say 10 years are a very wide time frame for new space. We want to be a lot faster. And personally, I want to see our technology, I would say, within the next 3 years already in space. And based on what we already achieved, it does not seem to be very unrealistic to me. So, yeah.
Thank you so much. Then we have a question for all speakers from Marvin Kuhn. Considering the ISM, are there approaches to minimize the destructive effects on the machines of atomic oxygen in terms of sustainability?
Yeah, probably I can answer. Yeah, so it usually brings a very fast oxidation reaction, sometimes impact critically on this. I think a passivation of the surfaces would be is one of the ways to do, and there are methods already in industry quite sustainable. When usually it's coated with nitrides or another metal oxides that are neutral to impact of atomic oxygen. If this is polymeric structures, this is more challenging, but even polymeric structures, there are some that can resist to impact of atomic oxygen.
Thank you so much. And please chime in if everyone else has something to add. But for you, Maxim, we have another question. So your technology is supported by 3 universities. What role does these universities play in your development?
Yeah, that's a good question. Thank you. We actually started the development of the technology, I would say within university, but outside of university. So that was, I was a postdoc and my co-founder was a PhD, and we were obligated to report and then walk through this path. After we left university, we found the company. We continued to work with one university, FAU, and actually slightly engaged in SAS. We got few European projects, so this collaboration helped us to raise a large amount of funding to build our first machines. And we, in our case, we engaged them for certain particular tasks, but we didn't use university environment as much as others would imagine. That we grew the technology inside the university, and then it was well developed, and then you need to commercialize. It was actually opposite, and I think our case quite good because we had idea. We used universities as resource for certain part of the development, and we didn't depend on them and their kind of way of working. We had our own way of working, and we use them for certain needs. So that was quite beneficial, I would say.
Thank you, Maxim. And another question for all speakers. So what do you think about the Made in Space attempt to patent the in-space manufacturing process? Is this maybe a game changer or a barrier for European startups?
I'll comment on patenting generally. I mean, we can spend a lot of money on patents, and it's questionable what the value is that's being created in that. For a startup, you don't have the resources to go out and sue somebody for a patent. They're really defensive mechanisms. If somebody sues you, then you have something to trade. That's the usual reason that you get patents, is to make sure that that you're protected in that way. When you patent something, you can patent a process or method. You just definitely can't take something and just slap in space on the end of it and assume that it's novel enough to get through the invention requirements. However, if there are processes that you're inventing or methods that you're inventing, then they can be patented. If that's a blocker on an industry or a new method, then you're in a pretty powerful position. But that's just par for the course in any industry. There's no magical space pixie dust in patenting or patent strategy or the approaches to patents. So I don't know the specific made in space patent, but generally I'd assume every company that's active here has a patent strategy, and it's mostly around being defensive, and they'll be patenting the things that are critical to their processes and being able to do manufacturing in orbit in the way that they intend to do it.
Thank you so much for that answer, Daniel. And moving on, we have a question for item 4. Are you looking for funding or pilot partners?
Yes, actually, during the last 2 months, I applied for 3 funding, and because I'm at the beginning of this startup and I need to funding to expand my my business. Yep. Is there anything?
In terms of pilot partners, do you have anything to add there as well?
Right now I'm in contact with the Innovation Center in Munich, but yes, I also thinking about the pilot partner. Yeah.
Thank you so much. Then we have, I think, one more question, which is, how close are we to have a globally accepted standard connection mechanism for orbit servicing?
As a company that's developing a refueling interface for spacecraft, it could be used for attaching payloads and things, but its primary purpose is to refuel. We just announced recently the open license for that fueling port. We believe that that's what's important. That's what our customers have been asking for, is to make sure that they're not locked into vendor lock, that there's multiple suppliers and things like that. There are different companies building different interfaces and standards. Well, nothing has emerged as a standard yet, and standard is a legally loaded term. But in terms of de facto standards and things that are being adopted, the best interfaces that provide the right solutions are going to be the ones that get accepted. And we still haven't seen anything, I think, emerge in that area yet, but it's coming, and a lot of people are paying attention to it. So I'm pretty optimistic that over the next 5 years or so, we'll actually get to try a lot of these things in space and figure out what works. And then what works best is going to be what's adopted across the industry.
Thank you so much, Daniel. And Sonali and Ulrich, I think I'll pass it on to you. Now we are out of questions from here, the Q&A.
So thanks a lot, everybody who asked the questions, and to the speakers and panelists for providing our insights on all those questions. We have come to the end of our webinar, but just before you sneak out and close your Zoom, I have Ulrich Olsen here, our counsel and research and innovation attaché. One of the parts of his work that he also does is bringing the industry and the academia together and finding out ways through his industry on campus collaboration initiative within ICDK, exploring how these can be done better. And so Ulrich is also responsible for the research and innovation side and for universities. So he has something to share with you guys, which would be our next steps.
Yes, so also from my side, I want to thank you to all the speakers and all the attendees. My final announcement will be our next event, which is also held in collaboration between the Innovation Center Denmark and good collaboration partners here in Bavaria, more specifically with Bavaria, the cluster for aerospace and a number of other things. We are teaming up for an innovation talk and a matchmaking event on collaboration with a view to Horizon Europe. So European funded research and innovation projects. So it will be an opportunity for companies and researchers to pitch and to meet interesting collaboration partners with a view to applying for European funding next year. But the event will be held on the 9th of November. You have the link here. We will also send it out in our follow-up email, and stay tuned also on with Innovation Center Denmark and our collaboration partners here. So thank you very much also from my side.
So once again, thanks a lot, everyone. Thanks to the presenter. Thanks to our back in the studio, the team behind the screens. Thanks to everyone. Thanks to our partners and host, ESA BIC Bavaria and ASO Anwendungszentrum. And over and out, and see you in the next innovation talk.
Thank you.
Thank you very much. Have a nice evening.
Thank you.
Have a nice evening. Bye.
Bye-bye.
Thank you. Bye.